Yo, this is Elektrofreak bringing you another video about electronic design. Today we'll look at Eagle. Just looking at how to get started with a new project and adding schematic files and so on. So this would be intended for those who have never used Eagle before. As you can see, this is the start page here. You can look at documentation, libraries, design rules for when PCB is actually designed and checked for errors. You can also do scripts and cam jobs of what we want to focus on is right now. It's projects. These are mostly end stage activities that you do once you have your design ready. Of course, to get there we need to start a project, and it's very easy. Also, all you have to do is file new project, and I've created my project for today. This is just Eagle tutorial 1, and what we can do is open project. You need to open the project so that you'll be able to add things like schematics, board libraries, and so on. You can also add folders to better organize your work. So let's just make a folder called noob1. Of course, you can name this whatever you want, but I want to show you noob level design, because I had a request from someone in the audience who wanted to start from scratch, assuming no knowledge of Eagle, which makes sense, because the video that I made last time, in that video I showed you something that I already created, and then went through explaining how the circuit works. But today we'll go through actually creating a circuit in Eagle. So let's go to noob1, and of course you can then use schematic. Right now it's untitled, but then of course you can always save it, and you'll choose if you want to save in this context, or do you want to go into noob1 and say noob test, just coming up with noob, or names like that. But of course you're free to name it more something that's more descriptive. But of course, so now we'll just start. Okay, so here's your main schematic capture design screen. One of the buttons we'll be using a lot is this one is to add parts, and that's to delete parts. So we click on add parts, for example, get a whole list of inbuilt libraries, parts from inbuilt libraries. So you can then go and select whatever you want. Of course, it's going to take a really long time to find what you want if you open each of these sub menus and then try to find what you're looking for. So of course you can always put a search term like so. For example, I want to put a resistor. So we have a European symbol, resistor with a European symbol, so we'll just put this on, and I'll also show you the difference between the European and the US symbols. Well, this is pretty much the symbol for Europe. European symbol is this rectangle with two leads on it. These are where you connect this component to the rest of your circuit. And that's the American symbol, a bunch of squiggly lines like this. So that's the difference. So let's add this one. Of course, we can always, add this generic symbol right now and then choose what kind of footprint you want. So this is a schematic symbol. This is what you'll see in your schematic, which shows you which components get connected where and so on. And this is your footprint. This is your actual physical layout. This is what the component would look like when placed on a printed circuit board. And of course, this one, the symbol stays pretty much the same. Really, it's the same symbol for all of these various footprints, but of course you can assign various footprints depending on what size and what spacing you want for your parts. These are all through-hole components because they have holes that go through the printed circuit board, and you have these leads, metal leads from this so that go through these, and then this one gets soldered on the other side. That's called through-hole. But you also have surface mount. So this one basically has rectangular metal pads on the component, and then corresponding metal pads on the printed circuit board as well. So you could do this on the top or on the bottom layer, depending on your design. This one, as you can see, has no leads, so there's no holes being drilled in the PCB to accommodate this component. This one gets directly soldered onto the surface. Therefore, it's called surface mount. So, like I said, we could choose this, for example. And we also want capacitor. So what we'll try to do right now is I'm just trying to think of what kind of circuit to show. We could do a little low pass filter, very simple low pass filter. Low pass filter means it allows frequencies of low frequencies to pass through the signal through the system without any change in the amplitude of the signal, and it attenuates or dampens higher frequencies. Of course, I'll show you some simulations of such a filter in a program called LTSpice, which we can also open up right now. And if you look closely, it looks like there's also a way to import and export LTSpice files, simulations, to or from Eagle. This is probably something I'll be looking into in another video, because this is quite interesting, because I haven't done this myself. I mean, I've done them separately. I've done LTSpice simulation and Eagle PCB design, but I haven't done this. I haven't used this particular tool here. Design link, well, that's a good question. So apparently you can look for parts, and that's a really good feature, because then you can see a whole selection of parts that are available in real life, which is important, because you need to know what's available in the market when you finally build your product. And then you can see various options and availability, how many are available at the moment, and is that a unit price, or is there a minimum order quantity? There are some parts where you have to order minimum 10 parts, or minimum 50, for example. But this one is minimum 1, so that means you could just say I want one of this component, and you get it in the mail, and that's the price. And of course this is the technical specification, which you can see basically for every component. That's actually pretty cool. I would definitely use this while designing, so that way I don't have to keep switching to the browser to look up availability of all these parts. That's really cool. That's a very good feature to enhance productivity, I would say. But anyway, back to basics. I'm getting, now I'm kind of getting the feeling that this is becoming a little bit non-structured and non-linear. But yeah, I haven't slept much last night, so my brain is a little bit zoned out, let's just say. But yeah, we'll get there. We'll make a simple schematic. Let's say no. Could always get back into that one again. Yeah. So this is LTSpice, which is a circuit simulation program built by or designed by Linear Technology, which is a big supplier of various ICs or integrated circuits for all kinds of things. Now, what I really like about this tool is it lets you simulate all kinds of circuits very quickly and very easily, and it's also really easy to use, very intuitive key bindings and so on. For example, of course, you could always click on these buttons here to do your thing. This one is to add part, for example, or you just press F2. I just use the keys because they're all right next to each other, and yeah, I've just gotten used to doing that, just pressing keys. So of course, and suppose you want to insert really basic components like resistors and capacitors. You don't even have to look for that. You can just do R like that. And this one gives you predominantly US symbols. I think there is also a way to get the European symbol to show up, but it doesn't really affect the simulation as such. Simulation is going to be the same whether you use a European or an American symbol. It doesn't really matter. What matters is the are the values that you choose. Let's just put this R, and we can do C, and then F3 is to connect. So you can connect it like this. What we also need is a ground. That's your reference voltage in the circuit. And then now we want a voltage source. Now this configuration is a very simple low pass filter, and I'll show you in a minute how this works, what this gives you. And we'll do a voltage source as an input, and then just do that and drag it into field. Oops, sorry. That's okay, even if you always delete, correct yourselves by just pressing F5. You can see the scissors pop up like that. Let's try deleting the ground, for example. There you go. If you want the ground again, just click G and then do that. There you have it. F3. Let's just connect both components like that, and another G, obviously minus goes to G here. And now we can simulate a frequency sweep, meaning we can get this voltage source to go from a very low frequency to a very high frequency, and we can define our start and stop frequencies, which I will show you right now. Exactly. So we want to do AC small signal analysis. Now here you can leave it as a DC value, or you could leave it as small signal AC analysis. You can also provide series resistance and capacitance and so forth. What you're seeing right here is an ideal source where all these things are basically zero. But real sources, on the other hand, always have some series resistance and capacitance. So if you want to simulate something more realistic, you could given these values. So let's just do 10 milliohms, for example. No, which is actually quite an interesting topic. We could do a video about this series internal resistance, because that's a very important topic when you it's a very important parameter when you talk about batteries and generators and solar cells and all that kind of stuff. So definitely I could do a video about internal resistance and how that affects your design and so on. But we'll keep a fairly low terminals, so we'll just leave this parallel capacitance at 0. We'll do a 1 volt AC amplitude, and we'll just leave the phase at 0 as well. Now the other options are DC value. So you can study DC value of whatever you input here. You could do a pulse, so like square waves with different duty cycles. Duty cycle is the ratio of the pulse being high, ratio of t on to t period is the duty cycle of a signal. Just for information. Sine wave, of course, you can give a DC offset if you want. Obviously, most important parameter is the amplitude and the frequency, and if you want to delay the start of your sine wave. Anyway, this here is the phase. You could change the phase of your sine wave, shift it left or right by a couple of degrees, and that's the number of cycles that you want to simulate. And of course, you can choose to make this information using the schematic or not. Sometimes what happens is if you leave this on, and if you have lots of settings, this could clutter up your view. But since all we have is really we're choosing no function, we're just doing AC small signal analysis with a series of 10 milliohms. We'll just leave this the way it is. So that's it. So then you see your source information here. V1 is the source name. R. Let's just do random values now, and then I'll show you how to calculate R and C for a specific frequency. But first we'll just do random values so I can show you basic concepts. So it's 1000 ohms, for example. You could write 1000, or you could just type 1K. It's pretty much the same thing. So let's do 1K. And then of course C, we can say let's do, I don't know, 100 microfarad. If you want microfarad, all you have to do is type U after your value. You can also provide voltage ratings, RMS current ratings, and all these other parameters such as equivalent series resistance, inductance, parallel resistance, parallel capacitance. This is if you want to build a more realistic model. Of course, we'll just go with a very simple model right now. And this would even suffice at low frequencies for a simple configuration of this. Of course, going into high frequency filter behavior at high frequency is a whole different topic. I did have the chance to explore that while doing the thesis at university, and it can get a little bit complicated sometimes, which is why I'll do that some other day in a separate video. But for now, let's keep going. You could, by the way, you could also select a specific capacitor, a whole bunch of. Now these are all real components, yeah, and you could get these things with real values. So then you have a very nice simulation. But of course, we just leave this right now at this, at the generics, and I think the same is true. Yeah, exactly. The same is true for resistance as well, and the same for inductance. So what we want to do is basically measure the output voltage, and the output voltage here is taking these terminals across the capacitor. And now let's configure the simulation, and this is how you do it. Click on the simulate and control panel. Sorry, not control panel. You should know this. I've used this so many times. Edit simulation command. Exactly. Here we want AC analysis. You could do an octave or a decade sweep. So we'll do a decade sweep. So that means each step on the decade is 10 times the previous one. So you'll have, for example, 1 Hertz, 10 Hertz, 100 Hertz, 1000, and so on. So we want, let's say, 10 points per decade. You can do a start frequency of 100 Hertz, or let's say 10 Hertz, and then go all the way to 10 megahertz. So we got make that setup for us. We can place this anywhere, and just place it on top here. And of course, let's not forget to save. You don't want to lose all the hard work that you've done. All we have to do is run. So that runs the simulation for us. And you can see this one builds up our plot, but this is empty because we haven't chosen which signal we want to plot. But we'll do that very, very simply by clicking this, and this is a voltage probe. So this will when you do this, you can see in the bottom right corner, sorry, bottom left corner, click to plot VN002. So this would be node 002 of the circuit. You can also do that here. For example, do this remains, well, constant, and this one gives you decibels, which is a logarithmic unit. For that, I'll explain decibels shortly as well. Now what we want is, as you can see, this is already starting to filter at quite a low frequency. Usually you'll see a line like this, and then at some point it starts to go down, and that's your cutoff frequency. Therefore, this has a very, very low cutoff frequency. We could change. Yeah, we could make this 10 ohms. Yeah, there you go. Okay, there we go. So this one gives us a cutoff frequency. So now we can see how this filter works, right? And yeah, that's a better view, exactly. So this is the gain, meaning how much the signal changes in amplitude. That's basically a ratio of this output voltage that you see here across this capacitor to the input, V1. Okay. So 0 dB means it's a 1-to-1 ratio, meaning the signal is transferred unchanged. Phase might change, so means this signal here is out of phase with this signal. Of course, I need to then talk about phase as well, keeping in with the loop story. But anyway, so yeah, this whole area is called the pass band, meaning this is the range of frequencies that is transferred through the circuit without being changed, without the amplitude being changed. Okay, and at some point you'll see this start to change. So this would be defined as the cutoff frequency of this system. So this is about, in this case, it's about 160 hertz, as you can see in the 59 hertz in the bottom left corner. And then the greater the frequency, after this point, the weaker the signal gets across C1. So basically, you could connect something else in this path here, and that wouldn't effectively would not receive these higher frequencies, or would receive them at a very low level compared to this. Now this one has pretty much the same amplitude throughout the frequency range. So this is a very, very, very small drop as well, because of the impedance that we provided at the beginning. But yeah, like I said, it's really small. It's really vaguely packed. We're talking about millidecibels here. So that was basic low pass filter. Of course, what we should do now is show you how to calculate real value. So this one shows you exactly the same thing that we built. It's basically the same circuit that we built. V out or V in is the transfer function. So you could just give it a try here. Let's put in 100. We had 10 ohms and 100 microfarads, and then you can calculate the exactly like I showed you, 150, 160 hertz. Of course, frequency analysis, pretty much the same thing that I showed you. Pretty much the same simulation that I did. And this step response is how the system would respond if you give it like a sudden jump from here to here with sharp rectangular wave, and that's how this would respond. As you can see, it's slightly delayed, and because of the filtering effect. But yeah, that's it really. That's all I'd say about low pass filters. Of course, I can put all the links in the description. No worries about that. Yeah, so let's complete this schematic. So we have a resistance in place. We want to build basically the same thing that we did in LTSpice. So this time will be a real implementation of the simulation. Of course, nothing very complicated here. All we have to do is, this is a PMA capacitor, also a through-hole component. Let's just choose this one, for example, like so. Or you could be a pro and then go search for real components, which we can also try to do. Yeah, exactly. Now, of course, for this you'll need to know your values. Anyway, this here was just showing you how to do this. Anyway, here we need to connect these two. So for that, if you want to connect two parts, you would click on wire, or I would actually suggest doing a net, because that one shows you the connections between various points clearly. But of course, in this case, wire would be sufficient. We'll do a net just to be consistent with what I was saying. So that's a net, and then you could also extend this like so. So See, this one, using a net would automatically create this junction here, meaning this point is connected, to this signal. But of course, I'll show you what happens if you don't use the net. Well, nothing tragic really, except the fact that junctions do not get drawn automatically. Right? So now we'll do wire again and then do this. Of course, you might think it's connected, but you can't be sure unless you do this junction. You have to manually, do this. Then you know that these 2 points are connected. So yeah, anyway, that was just to explain the difference. So we'll just do a net connection then, so we have it all clean and consistent. Now obviously we need input and output. We have a whole bunch of options. We could do a B and C connector, and coaxial connector. What I'm talking about. For example, that's a BMC. We could do this like so. Right click, by the way, right click, flips the part, like, let me just, sorry, escape is to stop. Trying, again we'll do net, remember, always use nets in this case. Oh yeah, one more thing, it's always nice to have the grid being displayed, so it helps you orient all these things nicely. I would do dots, display on, and this is the size of space between each of the dots in the grid, and this is what happens with the spacing when you hold the Alt key. You could leave it at standard settings like this, or you could click on finest, then you get a very, very fine mesh like so. But yeah, this is kind of over the top, so overkill. We'll just leave it at 0.1 inches and 0.01 inches. Yeah. Of course, you can always change the millimeters as well. Yeah. Which we could do that. We could do that right now. So then you'll have to change it. The reason we left this configured in inches is there are many standard components with inch or 0.1 inch spacing. In any case, now we need to connect this. So again, to explain what this is, I right clicked and I clicked on package, and this is what it is. So this center pin is what you see here, okay, right, this connection in the middle, and this connection on the side is basically the body, this metal hollow cylindrical body. That's the ground connection in this case. To show you what this really looks like, just Google BMC. I should probably prepare my tutorials or lessons a little bit more in advance. I just decided I'll do this unscripted because why not? So that's the BMC. That's what I'm talking about here. This is where, and the one that we are doing is a female connector. So get like this, and yeah, there are many variations of it. So that's connected. Obviously we need the ground connection. Like so, and then we go back to nets again. and then like so. Now remember, these two nets are crossing. They aren't connected at any point, so there's no junction here, as you can see. They're just crossing without overlapping. Okay, that is an important thing to do. And then now what we want to do is copy this ground, paste this here, so okay. Now everything is connected. And now, if you want, we could actually do board design. Then we switch to board, we do loop test. These are initially placed outside. So how you go about doing this is, you just drag each of these things like so. You can do it like this. And this one, also like that. If you zoom into it, you can see what exactly is happening. We'll turn this around like so. We shall do this. Okay. Now we have to start routing. How you do that is click on route. And then be careful about which layer you want. So you want the top layer. So we'll do the following. That's it, and then those are connected. That's basically, in the real world. This will be a copper connection between these 2 points, and you can go on doing this. And sorry, oops, we don't want that. Yeah, just continue doing that, and there we go. Now these all go to ground. There is an easy way of doing this. What we're going to do right now is to place something called a pier. Like so. Make that around here, for example, apply, and then basically do something. Also, it's important to change this to ground. This thing has been labeled ground. That's fine. This VR. Let's call this. This one should be named. Oops. Yeah, so that's a bit of an issue right now. We can obviously correct that by just doing rip up. Rip up is the opposite of routing. You can, tear apart. Exactly. We'll just keep that like so. Now this one has to be named so that then this connects to ground as well. This has just been given an arbitrary name. We'll have to change that to TND. Now you can see all this goes to ground. Now we know where to go. So that's very simple, like so. And all these things, you could do traces like this, or you could just do something very simple, which is to draw a polygon, and you want this in the bottom layer, or you could do it in the top layer as well. No big issue. This is a really simple circuit. There's no reason to and of course name this ground. So, and then what we do, we put some rat's nest. Exactly, there you go. So now all this is connected, all these are connected to ground. This is a common ground plane. These have their connections like this. And that's it. That's a very, very simple PCB design.